All right, I guess we can start. Welcome to this new year's Autonomy Talks series. Today is my pleasure to have Georgios Bakirtzis, who is a PhD candidate in computer engineering at the University of Virginia, working with Professor Cody Fleming. Georgios' interests lie at the interface of modeling safety and security of cyber-physical systems and compositional aspects that characterize these disciplines. And today he's going to talk about his recent work on compositional cyber-physical systems, and I'm really interested about what we're going to hear. So, Georgios, without further ado, I leave you the stage.
Yep. Thank you for the introduction. Good morning or good afternoon, I guess, everybody. I am Georgios Bakirtzis, and I work at the Link Lab at University of Virginia. Today, I will be talking about my latest work and the work that composes the larger part of my dissertation, which is about compositional methods in cyber-physical systems theory. This sort of like research program includes many people that you can see in the papers that hopefully will go with the talk, but it stemmed from my interest in creating methods and tools for implementing safer and by implication more secure systems. One way of doing so that we see a lot is by predictive mathematics and perhaps logic for modeling formal requirements. This talk will instead focus on structural mathematics, which is how things are sort of connected and the behavior stems from how things are connected versus how things are. I am not a mathematician, so I will not approach the subject from a mathematician perspective of sort of like definition lemma theorem. I'm going to sort of explain the problem or where it came from informally and then show very little formalisms and category theory to get us going. I will leave everything else to the preprints. So if I can go next. So cyber-physical systems are safety critical. I'm not going to spend a lot of time on this because we all know it. If you have autonomous vehicles, or if we have like air traffic control, or if we have medical devices or UAVs, and those things are sort of controlled in some way, and that way it doesn't work very well at the interface of sort of like this digitally controlled but operating in the physical environment systems, then bad stuff happens. And one of that bad stuff that can happen is that we can actually have up to loss of life. And I believe that automation complicates the cyber-physical aspect a little more, but it also provides some opportunities, right, about solving these issues. But in order to do that, I believe that we need to start thinking about modeling and system science in a very formal way about how the components create the whole and what it means for things to be put together as far as the interpretation of the final system that will get created. So when I first started studying and being a researcher, I was really entrenched in this image, which is that the effectiveness of designing and building a system and the cost have an inverse relationship. When we are at the concept phase, effectiveness is highest and cost is lowest. And then as we go through the life cycle all the way to designing, building, and operating systems, the cost goes way up and the effectiveness of our decision goes lower. And that does not only relate to design decisions, that relates to anything we do to the system. So I wanted to work on methods that work sort of closer to the design phase, but basically follow the system design process throughout the life cycle. So cyber-physical systems are sort of this complex being or thing, and they are sort of, this is an ontology that got started in NIST when they first coined the term, and then since then it has been taken by Edward Lee at Berkeley, and I think this picture is very important to see what areas cyber-physical systems researchers work on. And you can see that all the way to the right to sort of like interoperability, or in the modeling section is where we care about, but we also have like applications and the hazards analysis and safety and security and how these things are connected. But I believe that in each of these leaf nodes, you can spend whole PhDs, you can spend whole research careers, let's say, only working on models of computation, only working on composability, but in the sense of like in one particular domain, let's say of hybrid systems, or only working in the security of these systems. And I wanted a way to not just relate composition to sort of like designing a system at one particular level, but I wanted to be able to relate sort of like these different views at the leaf nodes. So let's say If we have continuous and discrete behavior, how can we perhaps connect it to an assurance case or a safety and security model? So my initial work was rather informal, and it was sort of with this systems engineering perspective of we build static models in the systems modeling language, SysML, which you can see on the left. And I sort of wanted to model the dynamic behavior of the same system. And I didn't know, I mean, of course, you can go and do your static element in SysML and then your dynamic element in Simulink and say that those two somehow agree, or perhaps like invest in a particular platform and then have synthesis tools from MATLAB. But I kind of want to have a more general framework of how do we relate this notion of architecture that you see on the left to the sort of behavior that we see on the right. And I didn't have a way of doing that. The other thing was that I was also at the same time working in sort of Leveson style safety requirements, which are very informal but very useful. They usually have general requirements, general hazards and general losses, and it connects sort of like a hazard can lead to a loss, and a requirement, you know, sort of like the connection between requirements is between liveness and safety properties and all that stuff. But there's a quasi-formal framework. It is based on sort of control structures, where those control structures don't necessarily relate to a mathematical model. And I wanted to sort of like, okay, so we have requirements, we have behaviors, we have architectures. How do we relate all these things? What is one model that can relate all these things and connect them? And that's how I sort of like started thinking about this problem. And I believe also that when we're going through engineering school, at least in the US, we're sort of taught this scientific inquiry way instead of the engineering design way, which is, okay, so we're giving you a physical system, let's say an oscillator study, then we're giving you a laboratory method to get data, and then we give you sort of the theory for you to figure out what's going on. While it took me a while to figure out sort of the value of the system in engineering is how well it matched the model. And it's not something grander like, okay, so we have nature, how do we figure out how nature operates? Is we have control over how we design those systems. That's a very important aptitude to keep in mind, because if we're talking about, let's say, physics and compositionality, then it's a larger project than engineering, because in engineering, we can actually constrain our systems to what we want them to do and not to do, at least up to a degree of satisfaction. Another problem that I was working on was sort of like the semantic convergence. With how do we relate that we have this digital world, and if something happens, let's say, to a label transition system, this relates to some sort of linear time invariant system or something like that, or in reality, much more complicated structures, but there is this sort of relationship between them. And then how do we relate that to hazardous state or safety? Or at least in this talk, we're going to talk about how do we constrain those requirements that I talked before categorically over the behavior and the architecture. So what is category theory? Category theory is sort of this, there's this course, of course, by the ETH people, but like, to me, category theory is the connector of mathematical structures. And in math, it is very clear what that means. In engineering, it's not clear yet what that means. But if I were to sort of summarize for me what that means, is like that we can take a problem, let's say an engineering design problem in this case, and put each element of it in its natural setting, and then compose those elements to something bigger. So see the holistic picture, but be able to keep the parts, which sort of goes against the notion of emergence that we have in engineering, that if you put things together, just studying the things doesn't mean anything. But if we do everything categorically, which is harder than it sounds, then we ought to be able to connect everything in the right way to know, at least to a certain degree of certainty, that the system will behave in a particular way we expect. So we talked about SysML, we've seen MATLAB Simulink perhaps, and we have this category theory that sets things in the right setting. For me, category theory is sort of the appropriate tool for studying flow of information. And we have here the wiring diagram category, which represents systems as inhabitants of boxes. They're not the boxes, they're what lives inside the box. And then we have wires or channels of information flow. And this is nice in engineering because we already see things diagrammatically. Of course, there's problems with diagrams. If you have too big of a diagram in your modeling language and doesn't fit one screen, then we know all the problems with visual programming in that setting. but at least for seeing how things are connected in abstractions, in different abstractions, and maybe having a language of algebra in the background, but then being able to visualize this immediately in a language of diagrams, that is certainly very nice for being able to reason with increasingly complex systems. So we're going to work in this category that has these two things. And I'm talking about a category, but I haven't really defined it. So we can think of a category as having some objects. In this case here, let's say sets X, Y, and Z. We have identities, which means that if I have an object, I can always recover that object. And we have a way of sort of transforming between objects. And that means that if I have a way of getting from X to Y with F, then I can create an arrow. Now, if I have a way of going from X, Y to Z, then in order for something to be a category, I ought to be able to go from X to Z immediately through the composition of these rules. So it is the study of composition at a very fundamental level. So why do we care about this? Well, we have different kinds of categories. The most obvious one for cyber-physical systems might be the category of hybrid systems, which is not shown here, but we have the category of graphs, we have the category of petronets, and we have the category of Moore machines. The more useful one, I would say, in engineering, or at least in control, would probably be the Moore machine, because it's general enough where we can start modeling things categorically rather quickly. But petronets are useful too, particularly in safety. And we're not going to see any of these necessarily, but it's useful to see how a category usually forms a graph. And another way of thinking of a category is like a hypergraph with a lot of extra structure. And this extra structure becomes very useful when you're trying to sort of relate vertically the composition of, let's say, the things we talked about, like requirements, behaviors, and architectures. The second important element of category theory is the notion of a functor, of a structure-preserving map between categories. So here we have categories C and D, and we have a way of transforming all the objects of C to the objects of D through a particular well-known operation. And we have the way of doing the same with the morphisms of the operation, if such a morphism exists. I think a very easy example for functors is sort of the power set. If it is the power set, might be the power set, actually. I always confuse that. But it's basically like an operation in set theoretic terms of taking something and transforming into something else. Let's say of taking the power set, it's the list that's a monoid. And doing so in a very precise manner. So you can see here on the right, for example, the pictorial view, which is if I have a way of transforming objects A and B to X, then I have the way of doing C to Y, and then form all the morphisms in that category, then I can construct a functor. And that's where sort of functorial semantics comes in, which is the notion of I have some syntax, and I can always know in a very specific way how I can get the semantics from particular syntax. I think you've seen this picture before, because I think I took it from one of the talks that actually occurred in Autonomy Talks. And I really liked it because it sort of captures my problems that I have with abstraction, that, we sort of like move up the abstraction and we say, okay, Maxwell's equations does everything, but then you have all these other layers like digital logic, assembly language, bits and bytes, and eventually you get a picture on the screen. And the question really becomes here, how do we manage this abstraction? And one way of managing that abstraction is with functors in categorical terms. Another way perhaps is double categories, but we're not going to get into today. We're going to stay into the simple categories theory stuff. So what are wiring diagrams? Wiring diagrams sort of formalize pictures, and they don't formalize any arbitrary picture. The picture has to follow a particular way of operating. So in this category, the objects are sets. So it's a set labeled category. And sort of like every object has an interface at the input and an interface at the output. And the morphisms of, of that box, if you will, of the big box, is that if we sort of have a way of creating an interface at the beginning of the box and at the end of the box, which is what this happens here, right? If we take the thing that comes out of X and we take whatever comes from the environment into the big box Y, and I'm able to produce basically the interface at X in, and I'm also able to create the interface at X out, which is just the same as what goes out to the environment, then I'm able to sort of have this picture be very clearly defined and define the totality of the behavior of that very simple example, of course. But it can basically scale to arbitrary length as long as we can obviously reason about it. Another important element is the monoidal category. So you can think about this as providing a tensor product. And the only thing this means, okay, we have some axioms here, but the only thing it means is that now we can do sort of operations in parallel. This is very important because when we have systems, we don't only work serially. A system doesn't just do, it's not a serial program. Sometimes we might need to take a sensor reading from one thing and also take a sensor reading from another thing before we use that information together. So at this point, we haven't talked about behavior at all. And there's two notions of behavior. There's the behavior of the system that I talked about before. Here, we're talking about sort of like architecture and behavior of a particular diagram. So at this stage, the boxes are completely vacant. The only thing you see is basically those wires and those boxes that are in here. And we don't know what X, Y, and Z do. So if we have an example of this, it means that what do we do at this stage is if we have, let's say, a box X, Y, and Z, and they're formed in this manner, the question is like, how do we get the composite behavior, but we don't have a behavior yet. So we're only getting basically what the picture on the top would be representing the wiring diagram, which it looks more like the bottom. So here we say basically like, okay, take all the things I expect and give me those interfaces for the whole box A. And it's the same operation as before, but this is not really a wiring diagram. We can draw things this way because it's useful to us, but this is. So in order to assign behavior to those empty boxes that we know how they're connected together, but that's the only thing we know, we need the notion of a functor, but sort of like lifted into the monoidal setting. And that's the only thing you really need to know, is that this functor basically preserves things even if they happen in parallel. So we have this notion of a box here with the interface that we saw before. And now we want to sort of like assign a behavior to the whole system A. But in order to do that, we have to assign something to X, Y, and Z individually first, which is sort of this red operation here. And it's the same operation here, as you can see. We take every interface and we provide some sort of behavior for that interface. And then we know how to calculate the output of that interface as well. So then we sort of calculate the composite of that behavior, which is the blue operation on the right here in the picture. And finally, we need to take each one of these things and do the parallelizing operation. So the first thing is we add behavior to each box. We take the composite operation of the behaviors of the boxes in a particular manner that they're wired. And then finally, we sort of like do the whole parallelizing operation to figure out the composite behavior of A. One sort of like example here is the standard controls model, although this has extra information. And normally, we don't really add stuff from the environment, at least not in the simple case. So what we need to do here is with horizontal decomposition, we're just seeing it, let's say, in the behavioral sense. So we say that I need to add a behavior to the box for sensor, and I need to add a behavior for the box controller, and I need to add a behavior for the box dynamics. On the right, you can see that it's sort of the same diagram or a similar flavor diagram like before, but this is sort of like the wiring diagram picture, and this is a picture we already understand. So we need to sort of like create the architecture, and that is what is this phi in, phi out does, is it creates the architecture of this diagram. But the other thing I want to show, especially to people that are familiar with control, is that here we have to sort of like add a behavior to each box. So when I first working with category theory, I thought this was going to be relatively straightforward. And it is once you figure out that you have to do this. But in this case, basically sensor and controller need to also take the form of the standard linear time invariant system or any kind of control system we choose. So if we choose more machines to describe our behavior here, every box here would have to be a more machine. What that means is that L and C here basically have to be trivial functions, because otherwise the thing doesn't work. Everything in the box that comes for category theory needs to be the same thing in order for it to compose in this horizontal manner. So what do we do first? Well, we add this sort of notion of xk plus 1 and yk to each of those boxes in a way that it works. And then we sort of do the parallelizing operation, and then we finally get a behavior, in this case, of a UAV, although obviously the picture is general enough to be a general class of control systems. So that was the example in the paper. So the second thing is like vertical decomposition, which we said in the beginning that we want to sort of relate behavior and architecture together. And for me, this is important for several different reasons. One is that we're going to talk a little bit about security later on. And this is a topic where architecture is really king. I mean, there are state resilient approaches to security, but we're going to see it from the perspective of like modeling security, but modeling security with real data at some point. So what is the slice category? You can think of the slice category as breaking each of the arrows in our previous notion. And by doing that, we can sort of say that, okay, these are the elements that exists in the box sensor, and these are the elements that exist in the box controller, and these are the elements that exist in the dynamics. Obviously, if I was, let's say, a mechanical engineer, I might have spent more time to describe the airframe of the system, or describe some other part of the system if I was an aerospace engineer. But since I'm a computer engineer, you can see here that the most granularity happens in the electrical system. The good thing about this is that if you had knowledge from an aerospace engineer or mechanical engineer, you could add this in the proper way and it would still be compositional in some sense. Okay, so we have sort of addressed behavior in architecture in a way that we can work with at this stage. What about requirements? Well, one way of dealing with requirements is through contract-based design. And we would certainly like to talk about these contracts in the same manner that we're able to speak about behavior in architecture. The difference being is that contracts don't really sit at the top. They're not like requirements at the top, behaviors and architecture at the bottom. They're sort of like, okay, a contract restricts the behavior, which then ought to restrict the architecture. That's why it's sort of like different from it, and we can't really visualize it in a very particular way because it's going to operate in each of those diagrams we saw before. So in every box, we assign this relation of what the restriction is at the input and what the restriction is at the output. So if I have the input and I know the input is within a range, I know what the output is. If I don't, then I don't really know anything. That's the problem with contracts. So to each box, assign sort of this pullback, this scary mechanism here, that the only thing it says is that I have the most general definition of a restriction or of a contract. And given that I know how to calculate that restriction or gain that restriction at the input, I will always know how to calculate it for the output. So at every given, if I do this properly for every subsystem, I should produce a huge composite contract that works properly. So what is a very simple example? A very simple example is that I assign a restriction for X, Y, and Z boxes, which were the ones we saw before. And I say, you know, the 4 to 5 here is the sort of input, and the 4 to 5 here is the output. So X and Y don't really do anything. They take, if the input is between 4 to 5, X will always produce 4 to 5. If the input is 8 to 9, Y will produce 8 to 9. Here we can see something more complicated, which we say, okay, so Z takes in 3 inputs. So you can see those inputs here, and this is the output. So it says if my first input is between 3 to 5, which it is, and my second input is between 7 to 9. And then I have an arbitrary input coming from the environment that I don't care what particular number it is, but I want to be a number. Then I will have an output of 0 to 1. And I have a way of basically creating this composite contract by saying, you will never get a 7 to 8 because your inputs never will produce 7 to 8. So we have the composite contract for the whole system. The interesting thing about this is that it generalizes over assumed guarantee contracts, if you've seen those, because it doesn't require sort of like labeling of the interfaces in order to work. So here, the only thing that we care about is that the types of the wire agree. So in the sense of like when you're connecting X and Z, the wire that connects them should be the same type. So the whole idea in the beginning was, how do we start from a system model and sort of like create this unification of requirements, behaviors, and architectures. I will say that how we do this right now is this picture here, which is, in a given process, we model the behavior of it, and then we might actually calculate some contracts, but semi away from our notion of modeling behavior. That's what we've done thus far in the categorical setting. We haven't done anything new in that certain sense. So in order to do something new, we need the third important element, or the third basic element, if you will, of category theory, which is a natural transformation, which basically says, if I have, let's say, two algebras, if something happens on my algebra on the right, I have something to say about the one on the left. You can see it here is that we have a plane of sort of functorial operations, and we can actually relate precisely how those are related if we can construct a natural transformation. In practice, this means that I have a way of taking the algebra of behaviors, and I have the way of taking the algebra of contracts, and know how my behavior leads to my contracts. I believe this goes the other way around as well, but I haven't shown that. So if you change something on your contracts, well, you ought to have something change in your behavior as well. And that's the sort of notion of unification that I see categorically, is that we have those requirements on the right and behaviors on the left. And if I change something on my requirements, I know what happens to my behavior. And if I change something to my behavior, I know what happens to my requirements. Obviously, this is much more complicated in practice, because that's where we need expert input. But for right now, this is the theoretical framework. So, and I believe, basically, before I go to the next step, that by using this framework and by perhaps coding it into a modeling language, we're gonna lead to safer systems if we have the quantifiable, at least, requirements in some form of formalism connected between behavior and contracts. And obviously, because we have a connection with the slice category between behavior and architecture, then those requirements can percolate all the way to synthesis. And that synthesis does not need to be in a particular manner. If we know what certain behaviors break down to certain parts of the system, we should be able to say, okay, so this contract applies to the sensory system, or this contract applies to the controller, or this contract applies to my dynamics. Again, the problem with contracts, as far as requirements engineering is going, is that if something happens to my environment and all of a sudden I get values that I really don't expect, the contract-based method will not really do anything for me, because it expects a particular input. And if it doesn't get that input, sort of the behavior of the system is undefined. So the second portion that has influenced my work has been that today, there might be security without safety. There certainly is security without safety, in the sense of like IT systems or something like that. But in the largely connected systems we have right now, either, let's say, an autonomous vehicle connecting to some sort of system in order to get over-the-air updates, but then the whole system is connected to the CAN bus, and it's sort of a mess. And there is no safety without security in this setting, right? In cyber-physical systems, especially the ones that are connected to something and they're not sort of like operating only locally, we need to be careful about how we model security. So one of the examples happened actually, I guess now 2 years ago, though I will still say last year, with Triton, which basically took control of a petrochemical plant's safety systems and disabled them on purpose. So it's not that, we have Stuxnet, we have other examples of malware, let's say, that have caused safety problems, but this particular malware literally existed just to cause a safety violation. So we want to be able to also talk about security in a manner that is compositional. And okay, this is kind of out there in the sense of like, obviously category theory is not going to help you with all those emergent effects. And I kind of want to show that is that any modeling framework is really not going to account for the fact that, okay, a ransomware attack happens to a hospital and I need to move a patient to another hospital and then I don't have enough time and they die. That's sort of the limitation of any modeling framework we have right now for security. So we have this notion of modularity in system design, but not only in system design, but in security as well. And you can think of sort of category theory as assisting with this modularity. But in the end of the day, if we don't have any way of sort of like testing for security in this setting, it is very likely that we're going to end up in this vicious cycle, right? That we sort of create silos and then break the silos and then create silos, because we can't really win in the battle of safety or security, for that matter of fact. So what are we trying to do categorically here? We would like to see how security can be assisted with the notion of the unit lemma. I know the unit lemma is a very difficult thing to grasp, or it takes some time for us to understand it, but I think for engineers it is very intuitive. If two objects agree under any possible test we can perform, then they behave the same. That's all we need to know. And that is very useful, because I believe that a large part of what hasn't been modeled in security is not just the effects of an exploit, but how attackers actually operate, which is that they don't really, go in and maybe they do have an arsenal of attacks, and they go in and they just randomly and blindly apply those attacks to sort of cause an unsafe scenario, or just, get into the system. They sort of like spend most of their time learning about the system. So learning what the system is, how the system is composed, what parts are composed together, and they sort of move in this way through the fog of war, if you've ever played a strategy game. So the way to do this categorically, now that we have the unit lemma, is that we have sort of this notion of learned behavior and learned architecture, of course, but we also have the learned behavior and learned architecture are defined as well. So what does this picture mean? It means that the attacker has a mental model for the system they're trying to attack. They sort of test that system with their knowledge, let's say by using a particular tool that checks the network or something of that sort. And then they get a new mental image, and then they go to the architecture. So they learn the behavior of the system, what the system is doing and what the system is not doing, perhaps what is not doing right, so they can exploit it. And then they try to learn more about the architecture in order to get into it. And we have a particular way of talking about this as a sort of like tests on the behavior of the system, and then tests on the slice category of the behavior of the system, which is the architecture. So what does this really mean? It means that if we have a real system which is on the left, and this real system adds some redundancy, we have 2 IMUs instead of 1. And then we have a sort of like attacker mental image of that, which doesn't have 2 IMUs, it just has 1. Those systems, I would claim that in some level of granularity are behaviorally equivalent. And it doesn't matter if the attacker doesn't know that, that there are 2 IMUs instead of 1. And that is important to be able to capture in modeling frameworks, to add sort of like this allowance of what the modeler might expect the attacker to know versus what the attacker might actually know. And we can do this for many things. Of course, we have to show that those systems are behaviorally equivalent, and you can go in and show that, 1 IMU is sufficient to fly the plane, therefore it's behaviorally equivalent, all that stuff. And generally the argument is a little bit more fuzzy here, but this is what allows us to do if we do attacker modeling this way. So there are 2 ways of using this framework, and they sort of naturally follow this wiring diagram way of thinking. One of them is to sever or otherwise change what is coming in through an input. So you can see here that the GPS has a completely severed wire, and that's what a rewiring attack does. It says, okay, I have a wire here that is coming from the outside world, and I have that wire basically cut, let's say by DDoSing the system at the GPS, or by doing something else, by doing GPS spoofing. And this is actually an operation that happens in the wiring diagram itself, right? It's sort of in the part of the architecture of the wiring diagram we talked in the beginning. We just change the wire. And that's one way of attacking the system in this particular modeling setting. Another way is to sort of like hijack a component, let's say change the firmware, or have some exploit that goes in and changes how the data is handled by the GPS or something like that. And that here you can see goes basically into the box. So here, for example, when I say cat here is the category of categories, which the objects are categories and the morphisms are functors. And that's the most general category in this setting that we're going to use. And basically what it says is that given a wiring diagram, you have a way of going in the behavior of that diagram, changing that behavior and coming back out. That's all this left diagram says. Okay, so the point of this is that in the end, we have a system that we have built compositionally, or a system model that we have built compositionally. We have a system that we can sort of restrict its behavior to a particular element. Then we have a way of like having an attacker have an erroneous version of that system. But in the end, the system is attacked all the same, right? They chose to attack the GPS. The system is gonna operate in a way that we don't expect. The problem, of course, is that what if they chose to attack the IMU? Well, then, you know, you have a second IMU and you don't have a third one, so you don't know which one to pick. So if you had 3 IMUs, maybe that would be a valid argument, but it isn't here. But definitely we would like to develop this argument more about why this is important to know if the attacker has a different image, what does it mean for the modeling and the defender. So this is unfortunately a very general setting because we would like eventually, you know, to put some sort of like, if you have a state machine or a Moore machine as your behavior, we would like to be able to speak very precisely about what the attacks do to that Moore machine. But as of this point, you could even say, okay, I have a ground control station that communicates with the UAV system, and I am able to do a social engineering attack. So it's not really practical at this point. It's not very impressive in that sense, but it is impressive from the perspective of that we can even do security modeling this way, which sort of stemmed from my being unsatisfied with just having a graph theoretic version of what attacks apply to what system elements. So one of the criticisms of category theory is that it's abstract nonsense. And perhaps, yes, if you're expecting to go into a field and change everything, change their notation, change how they model systems, then yes, I would agree with that. But I believe that by looking at things in this compositional manner can lead to new and exciting sort of expressions of one particular domain. So the new algorithm is probably the most used at this point, I think, dimensionality reduction technique. And one of the criticisms of that was that half the initial paper had category theory. And, you know, the first author said, you know, I came up with it because of category theory. And the end result was that the paper that was actually published didn't have any category theory, but it still remains true that without category theory, this person couldn't have come up with that. Obviously, dimensionality reduction is not my area, but I think it's interesting to keep that in mind as we go into and try to figure out how categories are useful in engineering and in control in autonomous systems. Is that maybe it's not going to be that we come into a radical conclusion only categorically, but it might actually show us in problems that we already have what the solution might be for these problems by working in this compositional manner. The other thing is that a driving force for my work is that software drives the development of theory. And now we have exciting new frameworks where we can actually model and talk about these things in a computational way, in a repeatable fashion. One of these is CADLab, the other one is IdrisCT, and I think there are a couple more now. There's even one for Mathematica, but this is probably the most popular one at the moment. And that is sort of like the right time to be doing this work because we can sort of actually create and model systems in this manner. So one of the goals of this research program is to have a modeling language that hides the category theory from the user, but uses category theory to show the user what they can connect, what they can't connect, what might be the ramifications of a contract not being satisfied, or what might be a security analysis framework, and we would like to do that in software. Evan Patterson and Halter here have actually created an epidemiological modeling framework in CADLab. So it's mature enough to do this. This is rather recent. This was 3 months ago. And that's a new development. If you were to play with CADLab, let's say over the summer, maybe that wouldn't have been as possible. So the final thing that I want to leave you with is that for me, composition does not come for free. When I first started this journey of learning about category theory, of trying to solve a systems engineering problem in a way that I didn't know how to solve in the beginning, I thought you could go sort of from the first house, which has a wall in the middle, to the last house, which doesn't have a wall in the middle, without going to the middle step. Oh, we can make arrows and have requirements mean something. And that has happened, actually. If you look at some of the category theory work that comes out of systems engineering venues, they sort of skip this middle step. They don't really go into detail about what composition really means. They just say, okay, this is a pullback, this is whatever. By doing this work and trying to really come up with an example, which is sort of the main result of the first paper, the first half of the talk, it was very apparent to me that you sort of need this crutches first. You need to put support in order for you to come out at the other end with a compositional framework. In this case, one of the important examples of this is that we need to have the systems that inhabit our boxes be of the same type. And that means sometimes that we have to reduce the mathematical definition of our sensor and controller to what it ought to be for the whole system, and see how we can actually make that so the whole system actually agrees mathematically. I think that a really good thing about categories is that they really haven't been examined much for engineering problems. We can potentially see this talk as being only in the wiring diagram. I believe that there is some sheaf theoretic stuff that the ETH group has done, but I'm not very well acquainted with me reproducing it. But the way I would see sheaves is that we can maybe have temporal logical specification, perhaps be able to capture safety barriers. And definitely, I believe that the notion of time, which is missing from my work here, but we're working on it, could be assisted with the Sieve theoretic way. Another sort of way to think about it is that we have Markov categories, and maybe we can do some reliability analysis there, or we can talk about MDPs. A secondary thing is the open games framework, which maybe can assist a lot in multi-agent systems. And finally, we sort of have like this enriched notion. Something that should have made you very uncomfortable is when I said the definition of the Yonedo lemma. I said like every possible test. In engineering, there is no such thing as every possible test. We cannot run every possible test. And we're working right now on enriched categories in order to say that there is a probability that a test is important or that a test is useful. Because in the current framework, basically, we assume that you can run any given test and you need to run vacuous tests as well in order for the Yonedo lemma to actually be true in practice. So all these things are sort of captured within the Talon project. And the whole point is to create this modeling language that we can compositionally build systems, and we can compositionally do some performance metrics for the systems. Safety, security, reliability are the first ones that come to mind. And thank you very much. That is my talk.
Thank you, Georgios. Very cool talk. Are there any questions from the audience? I have one, actually. So you talked a lot about the challenges in general that you will be facing, but what are the, let's say, next steps? The next steps for the next months for you. I'm curious about this consideration of time, for example, that you mentioned.
Yeah, so given that all of these things are happening with collaborators, the time thing is going to have to take a back step because of other reasons, but we are working on it right now. Is sort of how do we take these notions that are in the compositional cyber-physical systems theory work and add the notion of time, and perhaps even refine it to talk about what real time means in a compositional manner. And at the moment, there's two approaches to that. One is the one by Spivak, which uses sheaves, and I think you've seen it. Is like the temporal landscapes paper has some of it, I believe. And another way is sort of like with this notion of graphs, is that you split time in discrete steps, but you have a way at any given step to do different things. So that's the notion of time. In the notion of security, we have this notion of how do we make the unit element probabilistic, which is something that we're waiting for the mathematician to figure out how to do the unit element probabilistic, so then we can use it and talk about our security stuff in this manner. And the last thing that I am working on right now is starting to think about how do we model multi-agent systems compositionally within not necessarily the wiring diagrams framework, but within the category theoretic framework. So the two approaches right now is sort of like the open games that I talked about before, which is the invention of dual hedges. And the second one is more standard algebraic stuff, but be able to talk more general about how tasks compose in a multi-agent system. Those are the three things I'm working on right now.
Okay, thank you.
Georgios, well, first of all, thank you for the talk, and sorry I joined in late. Okay, so I really love this topic. I really love the this formalism and all the work that you guys and our group is doing in this area. So don't take the question as a challenge, but really as anyway. So let me just ask. So what do you expect to be the killer app of this theory, right? So what is the kind of thing that where this will make a difference? Things that this would enable that could not be done before.
If you asked me this question like 6 months ago, by the way, I don't think that's, we need to be challenging more ourselves with this stuff, because there's two camps right now, the camp that believes and the camp that doesn't believe. We need something in the middle, right? We need to sort of challenge our own views if we do believe in this thing. But if you asked me like 4 months ago, I would say that systems engineering and actually modeling languages for systems engineering is the killer application, in the sense of like, if we can, even go to the point of a company and they do all the coding to make it a professional system. For me, as a person that at the time was reading the SysML version 2 standard, it seemed that they were trying to do a lot of stuff that category theory gives you for free, but without category theory. And then you could see that it didn't really work out. So that would be what I would say 4 months ago. And I still believe that. I still believe that even like both academic and industry application of category theory is systems engineering. The second application that I see now, and that I'm really excited to learn more about, is that, I would say that I would position myself into systems theory or informal methods, not even control theory purely. I would like to see how perhaps in this autonomous systems world, we can talk about multi-agent systems that do learning composition. And if we perhaps, now I'm thinking very, loosely, but perhaps in 10 years from now, we can talk about the interpretation of learning systems in a system like an autonomous car. We can do so compositionally and say what would happen and restrict it the same way that I was talking before. All of these things are up to be seen. We have to prove that they're actually useful. We have to do the work, and that hasn't been done yet.
Yeah, thank you. Well, first of all, let me, I'm in the believer camp, right? But essentially the question was to try to think about how do we make the unbeliever change their mind, right? So what right? Because, we can keep talking in our bubble, and we're all very happy and excited about the work, right? But how do we reach out to outside of the bubble, right, and convince other people to use it? Now, I totally agree with you that actually when I talk about category theory or the work that Joel and Andrea and others are doing is systems engineering done right? So in a sense, I totally agree with that kind of vision. Now, so if you say that. So what you were saying that, like a few months ago, what you would have seen as the killer app is system engineering, kind of like a tool, right? So developed using category theory, right? But do you have an idea of what people are actually using, and what would it take to develop such a tool that would be better than people in industry are using right now to do system engineering kind of things, aside from spreadsheets?
Yeah, no, I mean, obviously the practical problem is that industry and government don't actually use modeling tools. They do, but they don't. But my experience actually has been very much in this field. I mean, I'm funded by who I'm funded, but we work with like, a modeling company like Vitec. We've operated a lot with. So we know how those tools get developed and how they ought to be used. But in the end of the day, all those modeling tools in the end are a fancy framework for database, right? I mean, at the moment,
right?
They don't
right.
do anything else.
The company right now, they use something called Polarian. I don't know if you know that.
I'm not familiar with that.
I don't even know what it is. I think it's something like a requirement tracking thing. But I kind of agree that the systems engineering side is it would be nice to have a nice tool or modeling language or something, but things they don't use it. But then you see that there is a disconnect here, right? Because we are talking about how we can get some very elegant, very powerful abstraction, formalism, to do all these kind of things, beautiful things, right? But then you have the practitioners who are not even close, right? So it's not that they're using a tool that is worse than ours. They're not using tools, right? They're doing all these things by hand. So how do you convince them?
Yeah,
I'm not asking you. I think that this is for us.
I mean,
is a challenge.
I think that's generally a problem, right? When you're proposing something new. When we are proposing something new, my other project that I was working on is sort of like a resilience project, and it's a resilience project that's very practically inclined. And the question there, I'm working with a very senior academic, and he's doing all these things at the end of his career to make his ideas actually take off. And it's a very hard thing. We can all agree in the academic community, believers or non-believers in the academic community, but how do you actually transition that to industry is a very difficult problem, right? But I agree with you that in order for this to be successful, for me, it would have to be used by people that are modeling, not necessarily the people that are doing everything with pen and paper and they say, I'm never going to touch a computer in order to design a system, but the people that do use modeling tools should be able to see what benefit this gives them. And if they are not, then this is unsuccessful in my book.
Yeah, but you see, there's really the key here is a modeling tool, right? So essentially, then you had to make the point that if you use this modeling tool in your work, you will be more effective in whatever way, than you will be otherwise.
And I think we have indication that that's true. I don't, I mean, I think that if you look at the collective works that are coming right now in this area, we have indication that this is going to be useful if it is done well. So then you're getting into the area, okay, so we have theoretical work in category theory, but then there needs to be sort of like human-computer interaction work, or however they call it in industry, in order to figure out how we can take these theoretical ideas and present them to a user, right? That's another aspect of where this might fail. So there's definitely a lot of work to be done.
So if I can make a comment on that, so when people say, so what we need is a modeling tool, they always forget to specify modeling tool for what. As good system engineers, we take a system, you can look at it from very different point of view, right? And so actually, my feeling is that, and well, there's a trade-off, right? There are methods that are very informal, where maybe you're happy about drawing boxes and drawing boxes around boxes, where the semantics is really not not very well specified, but somehow it helps your imagination or your communication. On the other side, I think there are things that are completely computable, where now you're not just doing like mental exercises of drawing your system, but actually you're expressing some properties of the system. And you see now that you get a little bit more closer to computability, then you see, well, I need different systems to model different things, right? So maybe they might have like a very superficial resemblance because they all have boxes and wires, but actually the semantics is very different, right? So you think about, oh, well, I want to model, my software models, how they communicate with one another, or I want to model, what are the fault trees in my application. Two ways to see a system that are maybe orthogonal, right? And so for me,
right.
you don't want to go towards like, oh, the modeling tool based on category theory, because by being so general, it will not have anything. It will not have, it will have boxes and wires, right? But you cannot do anything with it. So for me, the future is more like, taking different projections of the system in different directions and create a tool that allows you to solve, the queries that you have in that particular direction, right? So maybe one is the schedulers for real-time processes. That's a good example. Right? We don't use category theory, but those things actually exist. And then actually, for me, the killer app actually will be at a higher level, right? Because once you know that you have all different aspects of the system characterized using categories, okay, then now you can do second order category, right? By that I just mean, functors and things like that, right? So now you can think about how one representation maps to another, and things like that. So for me, it's so now, I don't believe there's everybody does whatever they want, right? So, but I would not be one to wave the flag of, all right, so we have a language to talk about everything, because if you talk about everything, you don't talk about anything, right? But I think it's more like, people in different domains coming up with, okay, so based on category theory, I have solved the problems that I have in this domain. And then when all these different people have solve their own, their own domain problems, then they can look at each other and say, okay, so maybe can we talk about functors between my problem and your problem, and things like that. So for me, it's a little bit more. Maybe it's a longer way before you actually have proof that these things are really useful. But also, Emilia, I wanted to ask you. You don't. For me, you don't have people change idea. There's the famous quote, which is science progresses one funeral at a time, right?
Yeah.
So for me, so that's why we do the class and everything like that, because you have to take them young, right? So you have to teach to the young people, and then eventually they will be the
right.
ones.
But then you need to have the young person coming in with this toolbox, right? And this young person should be more effective than the old person, right?
Yeah, of course, yes. That would be the the threshold to pass. Yeah.
Right. So in a sense, that I would say that that's something that you need, right? So then how the transition happened is, let's call about retirements, not talk about funerals, but
Yeah.
But in a sense, you have to show that you have one way of doing things that is more effective, right, than another way of doing things.
Yeah, definitely.
Yes.
But I think this is really like, so this is a very big change for me, especially if you put the computability in it and you say I want to go to something which is both elegant but also computable. It's really disruption, right? So you don't. I don't really expect the systems engineers worked at Boeing for 40 years, with whatever they use at Boeing to jump over this thing, right? It's. Well, I don't know. We're talking about the future. Who knows? But I think in general, it's more productive to just just go down. Don't even say, okay, I'm going to do things that you cannot do with your tool, like incrementally. I think you really want to win. You want to say, well, there are things that absolutely you cannot do with any tool like you have now, right? I will see whether this is possible or not, of course.
again, for a direct goal, if you read the SysML version 2 standard, and you read it, I mean, when it first came out versus the changes as it went, or you can ask someone that's familiar with how the standard was developed. I think a lot of the immediate goals present themselves. Obviously, in anything that has to do with engineering, we need to constrain which design problems we want to work on and stuff like that. But without having all these disjointed applications, let's say, I don't even know, like even having like IPython notebooks of showing how you put the semantics into the boxes. You know, that's what I'm working on right now. If we don't have that basic stuff, we can never talk about the big goal. You know, like we have to do the work first. And, you know, we can paralyze and say, yeah, we can't do everything, or yeah, we have to wait for a senior researcher to retire. But I think if you have a good idea, you should be able to convince people that it's a good idea.
Yeah, for sure, for sure. I guess my sense is that, you know, I think it's going to be a long way. You know, in your talk, I think you did a good job to say, okay, yeah, these are the exciting things that are happening in the community, and now there's this, there's that. But that's that's the beginning of the journey, you know.
For sure.
And the kind of work. So you know what I worry about is a little bit like, for example, like this catalog thing. You know, like if you say it as saying, okay, here's is a thing that we can use to talk about arbitrary categories, and yeah, okay, then that's useful for talking about arbitrary categories. But can you talk about any specific category in a way that is really, really effective? So for me, that is like, you know, I mean, we should place these contributions like in perspective, right? And I think what really, so, and I don't think that the kind of domain independent tools that you can create are really going to be the thing that are, you know, going to win the battle, right? I think it's more going to be like, yeah, go to a specific field and try to solve the problems there with the category theory, right? And the
Right.
problem now is that there's a lot of category theories that cannot do that, right? Because they're not domain experts.
Yeah, I mean, I think that a lot of it is like transcription of known results, and you know, it's definitely difficult to collaborate normally, but getting into such a barrier, I think it's difficult for people to see even what a concrete example of those categories would be. And that was actually one of my goals on this preprint, was to actually have a full example, because nobody does that for some reason.
Yeah, no, I get I know exactly what you mean, right? And that's why we're putting a lot of examples in the course, like really worked out examples. Yeah.
Right, great discussion. Are there any other questions? Or are we the only ones that remain? If not, I think that we can thank you, Georgios. I think you gave your email address if someone wants to reach you. Thank you very much for the great talk, and see you everybody next week to next Autonomy
Thank you for
Talk.
having me.
Bye.
Bye.